So we have direct, indirect, trivial, and vacuous at this point. One of the more useful, in my opinion, but weird methods of proof is a proof by contradiction. Now, a proof by contradiction asks us to look at the if-then statement that looks like this. When is this valid? If I have an if-then and it ends in a false, what's the only way this can work? Colin? So this part has to be false as well, which means P has to be true, right? So if I have an argument that starts with, suppose this thing is not true, and I end up with something that has to be false, the only way that argument works, is valid, is if P is actually true in the first place. Usually we're going to show this false to be something and its complement, but that depends on the thing we're trying to prove. And it's not always a straightforward behavior. So how would we do a proof like this? Well, I mean, I can go back to the ideas. Here's an example. We already proved this one, right? We used this as our indirect proof. We proved this by contrapositive on Monday. So I want to start with a different idea. The way I'm going to say it is, suppose something is not in here. So here's my proof. Suppose 3n plus 2 is odd and n is even. This piece right here, that's what I want to be broken, yes? That's the part I want to be false. So that's my not P-ish idea. If n is even, n equals 2k for some k integer, and that means 3 times 2k plus 2, well, that's 6k plus 2, that's 2 times 3k plus 1. What do I know about this? Inside the parentheses. Which makes this 2 something, wait. Three n plus 2 is even, isn't it? I can't have both of these things be true at the same time. I've reached my contradiction. I started with the idea, well, let's suppose this thing is odd and this is even, but if this is even, then that has to be, oh, there's my cup, isn't it? This is a clear contradiction right here. I'm trying to draw two arrows banging into each other. I can't do this. So our assumption that n is even must be false. Therefore, n is odd. And isn't that the conclusion of the theorem we wanted to say? if 3n plus 2 is odd, then n is odd. I was able to come up with that as a conclusion. Proof by contradiction is weird. It is an unusual method because it results in us saying something that sounds very much like the scarecrow from Wizard of Oz. In order to do this, you have to do that, but you can't do that, so you can't do that. Wait a minute, what? It sounds like it shouldn't work. In Latin, the name of this is to reduce to something absurd, reductio ad absurdum. What I've got is hey, this thing has to be even, but it has to be odd. It has to be even, it has to be odd. You can't do both. Out. The most famous proof by contradiction goes all the way back to Archimedes and the Greeks. Original Greek mathematics made an assumption, and the assumption was that everything that we measured was either measurable in units or in ratios of those units. And that's what a rational number is. A rational number is a ratio. Integer on top, integer on bottom. Irrational means you can't do that. I need to write down my definition, just like my definition for even and odd. Definition. A number is rational if it is expressed as A over B with A and B integers, B not 0. And really, I want to go a step further. And I want to say A and B have no factors in common. So technically, when I think of, like 3 over 6, that's the number 1/2. I reduce it to its lowest terms. A number is irrational if it's not rational. So, how do I prove my theorem? Well, the proof by contradiction starts with the following sentence. Suppose it is rational. Proof. Suppose square root of 2 is rational. Go back to the definition. What does that mean?
Expressed as A will be A1
So there exists A and B integers, B not 0, root 2 equals A over B. A and B have no common factors. Exactly. That's what my definition says. So far, so good? Take this expression, square both sides. If I have root 2 is a over b, then 2 is a squared over b squared. Well, that means that a squared is rearrange that. Aha! I now know something about a squared. A squared is even because it's 2 times some integer. B is an integer. B squared is an integer. 2 times an integer, that means even. I am now making a very big claim. If a squared is even, a has to be even. Now, that in and of itself is a hell of a claim. Because give me an even number.
4.
Square root of 4? Perfect. Give me another even number. How about 6? Well, shit. Square root of 6 isn't even an integer. I'm in trouble. How do I know that's true? That's why I put the asterisk on it. Because I don't know that's true, except I kind of do if I go back and I look at what we did on Monday. On Monday, I actually wrote a proof about numbers being odd and what happened with their squares. So I'm going to go over here and I'm going to write this little star. Note from Monday, if n is odd, then what did I say about n squared? This was our very first direct proof. Go back and look. If n is odd, then n squared is also odd. What's the contrapositive of this statement?
If n squared is even, then n is odd, not even.
If n squared is not odd, it's even, then n must be even. So I actually do know this, but I only know it because I proved it along the way. This is a perfect example of a lemma, a helpful thing I already proved earlier that I get to use again later. So I have to cite this. I can't just pull it out of my ass and say, oh, well, of course the square root of an even number is even. It might not even be an integer. But if it is an integer, I'm using this idea. Okay, wait a minute. What's it mean for a to be even? Two times something. I need a name for the something. Okay. There exists k integer with a equals 2k. Now I want you to take this and put it in here. So 2k squared is equal to 2b squared. What happens when you square the stuff on the left? Four k squared. I can divide both sides by 2, can't I? And that means that b squared is 2k squared. I have a problem. It's not a big problem, but here's where my contradiction comes from. If b squared is 2 times something, then b squared is, and if b squared is even, what does that tell me about b? Just the same way we did up here, I can now say b squared is even, so b is even. And that is where my contradiction comes from. Why is that a contradiction? Colin. And if A is even, it's divisible by 2. And if B is even, it's divisible by 2. And we said way up there, no common factors. And now you've shown me they're both even. And that means that the assumption I made at the very beginning of this problem is the thing that is wrong. What was the assumption I made? That this number is rational. So root 2 is not rational. It must be irrational. Please understand, to a Greek mathematician, I have just spit in the face of God. Because in ancient Greece, everything is number. Whole number or ratio of. How dare you give me a number that can't be expressed that way? Even Pythagoras' own school, when approached with this idea, had some of the students freak out so badly they left school. It is rumored that one of them committed suicide. I don't believe that to be true. It's a great story, isn't it? This shook their world so badly. Why would this shake their world so badly? Pythagoras himself said that if you take a triangle that is a right triangle, and this side is 1 and this side is 1, what's the length of that side? Root 2. But think about getting this. You have to go over and up and over and up and over and up and over and up, right? Well, how many overs did you do? I did enough to go all the way across, didn't I? How many ups did you do? So the length of this jagged piece is 2. Now make the steps smaller. The total horizontal and the total vertical must still be 2. This number is smaller than 1.5. How does that work? The only way Greek geometers knew to prove stuff was in geometric terms. And suddenly, you're telling me that the square root of 2 should be 2. That's bull. People were seriously shook by this idea. On the other hand, we today consider the square root of 2 a number. We have a decimal that approximates it, 1.414, and off it goes, right? But we found that root algebraically, not geometrically. The switch from geometry to algebra happened in roughly 800, 1200 AD, and is the response of one person. More on him later. The book, by the way, was called The Method of Completion and Reduction, Al-Yabar et Mulkabala. Al-Yabar. Algebra. Algebra. That's where the frickin' word comes from. Questions? SMA 240, Readings in Mathematics, covers the history part. Frequently, I want to show that two or more ideas are true together. In one sense, every definition is really an if and only if statement. A square is a quadrilateral with four identically length sides and four identically measured angles. If I see a quadrilateral, it's got four identically long sides and four right angles, it's a square. That's an if and only if, isn't it? But I hate trying to do these sorts of proofs, so what I really do is I split them up. An if and only if proof is really two proofs. That's it. It's just two of them, one in each direction. Show P implies Q and then show Q implies P. Now, you could do each of these parts whichever way you want. You could do this one directly and this one indirectly. You could do this one indirectly and this one by contradiction. It doesn't matter. But each one of these is now a single direction proof. If I have more items that I want to show are equivalent, say P1, if and only if P2, if and only if P3, well, I find it easier to go in a circle. I'll go like from P1 to P2 to P3 back to P1. So I'll really do three proofs. If I had four things, maybe I'd do them all four, one to two, two to three, three to four, four to one. Sometimes you change the order up because it's easier to do one way than another. But each of these proofs is direct or indirect or simple, I hope. My goal is to have simple proofs. Questions? Any universally quantified statement is false if I can find one value in the domain where the statement itself is false. Sometimes that's easy. Sometimes that's difficult. An example. Grab your calculators. I'm using a new term here, so I need you to tell me what it means. What does the word prime mean when talking about a number? Huh? So any number whose only things that divide it evenly are 1 and itself. 3. 3 is prime. The only things that divide 3 evenly are 1 and 3. 17 is prime. 51 is not prime, because 51 is 3 times 17. 6 isn't prime, it's 2 times 3. Pick a number. Somebody please pick a number. Say again? 50. Plug it in. 50 squared minus 50 plus 41.
2,491.
2491. Is that prime? We would have to try and divide it by something, right? It's not divisible by 2 because it ends in a 1. It's not divisible by 3 because when you add up the digits, it doesn't divide by 3. It's not divisible by 5 because anything divisible by 5 ends in 5 or 0. It's not divisible by 7, is it? Try and divide it by 7. That's the one I don't remember the formula for in my head. Is it divisible by 11? By 13? If I get up to 50 and I haven't found a factor yet, it's prime. But if you pick any number between 0 and 40, I guarantee you this will turn out a prime. I didn't know about 50. But I know that all the numbers between 0 and 40, this works. Plug in 41. Wait a minute. 41 squared minus 41 plus 41. Isn't that 41 squared? It can't possibly be prime, can it? Even though for the first 40 numbers I try, 0, 1, 2, 3, all the way up to 40, I never get anything other than a prime number. Hey, this is going to work. No, it didn't. So here's a problem. I might want to show something is true for all numbers. I can't just keep plugging them in and hope for the best, can I? I'd be in deep if I could do that, because I'd have infinitely many numbers to plug in. So what people often do is they try and rule out counterexamples. They try and show where counterexamples will have issues. Or, hey, if I can't do a proof completely, maybe I can get closer if I try and show where the counterexamples are going to show up. If I find one, I'm done. As soon as I find a counterexample, I can walk away and be done with this. To that end, there are a lot of open questions in math, conjectures for which we do not have a proof yet, for which no counterexample has been found. A positive integer number is a perfect number if it is the sum of the positive divisors less than it. I beg your pardon? Hang on a second. 6. What numbers divide 6? And 6 itself, right? But I don't count the number itself. I only count those less than it. 1 plus 2 plus 3 is 6. What are the numbers that divide 28? Okay, but let's take all of them, right? I got 4, I got 7, 2 and 14, 1 and 28. Got anything else? That's it, right? So throw out 28. What's 1 plus 2 plus 4 plus 7 plus 14? I'm not going to make you do this one. I believe 8,192 is also a perfect number. Here's the conjecture. Conjecture. Every perfect number is even. In order to prove this, I need some nice formulaic method of finding perfect numbers. I don't have one. So far, no one has found a counterexample. And they've checked numbers up to 10 to the 300th power. If there is an odd perfect number, it is bigger than 300 digits long. But no one's found one yet. So that's not proved. It's not true, it's not false, I don't know yet. The evidence weighs highly in it being true, but that's not a proof. And I'm certainly not just going to keep plugging in numbers and hoping for the best, because I have infinitely many numbers to look at. Online, there's a web page called Odd Perfect. If you Google this, you can find out how far they've gotten. They must have gotten past 10 to the 300th by now. I remember that from a number of years ago. So these numbers are huge. A conjecture is something we don't have a proof for. I might suspect it to be true, but I cannot claim it is true until it is proved. The other thing I have to be careful about when I'm doing proofs is not screwing up. The following is wrong. I hope you will all agree that the following claim is wrong. Does everybody agree that that's hopefully bullshit? Ready for a proof? If I have A equals B, I can then multiply on both sides by A. If I multiply on both sides by A, on the left I get A squared, on the right I get AB. Now I'm going to do the same thing on both sides again. I'm going to subtract B squared. I did the same thing on both sides. That's okay. Hey, wait a minute. Both sides factor, yes? This side, I can pull out a B. And on this side, how does this left side factor? Hey, wait a minute. I have an A minus B on both sides. Cancel it. Then I get A plus B equals B. But remember what I started with? I started with the idea that A equals B. So the left side isn't A plus B, it's B plus B. That means that 2B equals B. Divide both sides by B, I get 2 equals 1. I proved it. I'll loan you $1 today, you owe me 2 tomorrow. I beg your pardon? Okay, clearly I made a mistake somewhere. There's something wrong here. Where? What did I do that's wrong? Evan? I'm sorry? No, I'm using the standard ordinary definition of two numbers are equal if they're the same. I mean, I'm not changing any of those things. I did an arithmetic mistake in here. It's a very specific mistake. And I even rigged the way I was going to say it, rigged the way I hid it from you by saying it in a particular way. Colin? I canceled. Canceling is dividing. What's A minus B if A and B are equal? And if I'm canceling, I'm dividing by that thing. Right here. I lied to you all. I'm not allowed to cancel here because what I'm trying to cancel is a zero. And canceling is dividing, and you're not allowed to divide by zero. And if I can't divide by zero, I'm not allowed to cancel something that's equal to a zero. But I did it, and nobody blinked a word because you're all still writing it down, and I snowed you, just blew it right by you, didn't I? A proof of a theorem, the theorem's the headline. The proof is the entire article. You can't just read the headline. You have to read and follow the argument in the article. Now, sometimes it's, I think, a little more obvious, depending on the way we write our problem. Now, I happen to know this particular theorem is true. If n squared is even, then n is even. I'm about to write a bad proof. I want you to tell me why the proof is bad. That's the entire proof. That proof is wrong. I did something deliberately wrong here. What did I do? Yes, I do. I? The problem starts if n squared is even. Don't I start with n squared? Right? Keep talking to me. Where the hell did this sentence come from? It's not connected to anything above it, is it? It doesn't follow. This, I just pulled it out of my ass. This came out of thin air. That's referred to as a non sequitur, literally, does not follow. And a proof that uses a non sequitur, especially a non sequitur that is my conclusion, is referred to as a circular argument. If n squared is even, then n is even. Well, if n is even, but that's where you wanted to end up, not where you wanted to start, you can't start with, hey, this is true, so this is true. I didn't really do anything. I just kind of bounded myself in a nutshell and called myself king of infinite space. It doesn't work like that. The other logical fallacy term for this is called begging the question. I'm going to show my age again. It's a rather old song. It was a bit on Sesame Street and on The Muppet Show. There's a hole in the bucket, dear Liza, dear Liza. Am I the only person who remembers that song? A couple of you will remember this. Okay. The whole idea is that you need to patch the hole. Well, how do you patch the hole? You make a patch out of straw and mud. We don't have any mud. How do you get mud? You need to get water. Where do you get water? With the bucket, but there's a hole in the bucket. Go round and around and around and around. A circular argument. Same idea. Questions? These are, for the most part, the most commonly used models of proof. But there are lots of other places where a different method is useful. Sometimes there are particular parts of my argument that are easier to address based on things I know, or maybe I should divide my group into some sorts of subsets. Again, I'm going to go back to Archimedes. There is something called the Archimedean method of exhaustion, which really Archimedes didn't invent. A guy by the name of Eudoxus invented it, but Archimedes wrote the book and gets credit. If I have something that's only true for a small number of values, a finite domain, remember, a universally quantified statement is a giant and statement. So, claim 2 to the n is less than or equal to n squared plus 1 for n positive integer n less than or equal to 4. I want to prove this. How many positive integers less than or equal to 4 are there? 1, 2, 3, and 4. If I show it's true for those 4, I'm done. There's no reason to do a general style proof if I only have to look at 4 things. Show me it works for those 4 things. Those are my cases. My proof is 4 cases. N equals 1, n equals 2, n equals 3, n equals 4. And literally all I have to do is plug into both sides. What is 2 to the first? What is 1 squared plus 1? That's also 2. Isn't that less than or equal to 2? I'm done. Do it for 2. 2 squared is 4, but 2 squared plus 1, that's 5. Well, this side is definitely less than or equal to that side. For 3, 2 cubed is 8. 3 squared plus 1, that's 9 plus 1, that's 10. That inequality is correct. Do 4. 2 to the 4th is 16. 4 squared plus 1 is 17. That's true. Done. I have verified my statement for all of the cases applicable in my domain. Now, some proof by cases are absolutely huge. If you have a minute later on, you should look up something called the four-color theorem. The four-color theorem says that if you take a map, any map of anything that you can draw on a flat piece of paper, I don't care if it's a real map of the world, if it's a map of Jupiter, if it's a map of some made-up kingdom, I don't care. There are only a couple of rules. Each country is a contiguous object. No country can have multiple pieces. We'll count those as separate. So Alaska is kind of screwed in the United States of America. Countries share a border if they share a straight line piece of border, not a corner. So if two countries only touch at a corner, we don't care about that. And you have to be able to draw the map on a flat piece of paper. If those three rules are observed, you need at most 4 colors to color it so no two touching countries are the same color. This was conjectured in the 1800s. And people proved you didn't need more than 5 colors by the early 1900s. But they couldn't prove 4 colors until the mid-1980s. 2 guys by the name of Haken and Appel broke this down into a proof by cases with 300,000 cases. They ran it through a computer. It was one of the first computer-aided proofs ever. And it was done to get the statement that you only need 4 colors proved. Since then, people have reduced the number of cases required. I think right now the version of the proof that exists only needs about 8,000 cases. I did 4. I'm not doing 8,000 anytime soon. But I like this proof by cases. It exhausts all my possibilities. And that's why we also call this proof by exhaustion. There are some other ways to address proof by exhaustion. I will look at those on Friday. Officially, we have finished section 7 and are starting section 8. And that makes the homework for section 7 due on Monday, 2 class periods from now. I will see you all on Friday. Have a wonderful rest of your day.